Right, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and very good day, everyone. So today I'm recording without my face, okay? Because my wife has another meeting running concurrently. So if I were to record the lecture with my face, I need to stay outside with my desktop, and therefore I will record all her conversation, which might be a bit restricted. Therefore, I moved to a different place where I can just talk to my iPad while do the recording. So I cannot have my face, unfortunately. Okay, so today we will look at the final bit of topic number 2. Okay, so topic number 2 still covers about enzyme. Today we're gonna look at enzyme activity. Alright, so what have we covered so far? So the first lecture we've looked at biotechnology, first lecture or the first topic, I would say. And then the second topic we looked at enzyme in general, or as what I like to call it is in vitro technology. Okay, so enzymatic technology, enzyme technology, in vitro technology. So those are, I would say, the same. Because they are all classified under something that you can do in the lab, in the chemistry lab. So to say, you're going to extract out the enzyme, and you will use the enzyme only without using any different types of biotechnology. Okay, so we looked at classification of enzyme, whereby we look at the EC codes. So today we're going to, if we have time, I will show you a little bit more on the EC code, where can you find it and whatnot. Alright, and then we also looked at the catalytic activity, as in the models that is involved, the kinetics, which is Michaelis-Menten equation primarily, and the selectivity, whereby we looked at the selectivity of an enzyme to a substrate in a few examples. And then we also looked at how to isolate the enzyme and how to purify them. So today, instead of looking at the application of enzyme in the industry, I want to go back a little bit and focus on the enzymatic activity just a little bit more, so that when we, of course, it will relate it to application of enzyme in industry, but the industry bit is not really highlighted, and this the highlight, I'm gonna highlight that together with the cellular technology, and hopefully by next week. Okay, so we'll just go through the lecture notes first, and we will see whether I have enough time to cover a little bit more or not. Okay, so the remaining lecture now will be enzymatic activity and biotechnology in industrial application, and because we have moved up the catch-up session last week, and of course we don't have enough time for the lecture. I'm trying to compress everything, because we will have our alternative summative, or you will have your alternative summative assessment on week 14. Okay, and the time now will be the duration for the exam, for you to submit your assessment, is within 24 hours, and this one has been approved by the department. Okay, so enzyme activity. So this topic has been mostly covered previously. So if you look at the lecture notes or the lecture recording under the title of catalytic process in spectrum, then you will see that it's related to those parts of the lectures. Okay, so previously what was covered are things such as the factor involved in enzymatic activity, such as pH, influence of pH, temperature, ions, and whatnot. So if you still remember where we draw this, so this one is activity, and so this one is either pH or temperature. Alright, and then what we saw was that a bell curve shape activity as you change your pH or temperature. Okay, so that's how they are related. But what missing during the previous lecture is how and why. Okay, so how do you actually gauge your activity? How do you get this type of graph? And why is it important? So I know it's important generally to say it's important to know this type of graph because enzyme works at a certain pH and temperature. What I'm thinking of is why you need to do this. Why do you need to know how to gauge this enzyme activity? Okay, so that's the why bit. All right. Alright, so I already have this. So previously what we have is, for example, if pH and activity, you will have a bell curve, something like this. Similarly for temperature, you will have something like this. Normally in normal scenario, the bell curve shape is not actually symmetry. Okay, so you might have a skewed either towards either side, towards the left or towards the right, because depending on the pi of the enzyme, so you might have a bit resistance towards a certain pH. Say for example, what can I say about example? Okay, so I'm not gonna talk about pH. So if you're talking about temperature, right? And we in our body we do have our own enzymes, correct? So the enzymes, our normal body temperature, as we were told since a long time ago, is 37 degrees Celsius. Even though some people might have a lower temperature, some people have a higher temperature. How do I know that? If you go and search for scan your body temperature, today because of COVID, when you go to any restaurants, you need to scan your temperature, and you can see that some people will have a slightly higher than 37 and some people has a slightly lower than 37, which is, so to say, still okay. But imagine when your body temperature goes to 38, which is the starting indicator of a high fever for some people. Okay, again, it's not the same for everybody, and definitely 40 is a very high fever. Okay, so when you're talking about this, where does actually the activity plot comes in? Okay, you can still see that some people at 40 degrees Celsius are very active, very very energetic, even though for some people at 40 degrees Celsius they are very very lethargic. So these are some of the indicators saying that it might be different from people to people. And also if you go down to about again, this one is more on internal temperature. This is not a surface temperature. Okay, so if you I cannot say that if you stay in an air conditioning room whereby the temperature that you set is 20 degrees Celsius, then the enzyme still works. No, it doesn't work that way, because the 20 degrees temperature that you set for your air conditioner is a surface temperature. So your body temperature should still stay around 37 or 36. Okay. Now, I think I should better stop mumbling about that particular lecture slide and move on. Okay, so the activity is a measure of concentration. Alright, so enzymatic activity, I'm sure, I hope that everybody have guessed this by now, or at least grasps the concept of the activity shown in all the previous slide, a measure of a concentration. Okay, so even though we are measuring the activity of the enzyme, but the value is a measure of concentration of either a formation of a product, okay, formation of a product, or a disappearance of a reactant. Okay, why cannot we measure the enzyme activity directly? Okay, because if you recall Michaelis-Menten equation, I'm just gonna do the short form. Okay, so you have the substrate plus enzyme, and then we will form product. Okay, so these are the most simplest one. I'm not gonna do the complex Michaelis-Menten equation. Now, what is happening here is that the substrate, say initially it has a certain concentration, okay, X, enzyme also has a certain concentration, Y, and then we also have a certain concentration for the product. But at the same time, what you do have is you will have an enzyme concentration whereby it regenerates, and this enzyme concentration is the same as that. Okay, so to measure the enzyme concentration, if you were to say let's measure the disappearance or the of enzyme entity, we cannot actually do that, because the optimum condition for an enzyme to work is as a catalyst. So it is not consumed, but rather is regenerated. So if you were to regenerate an enzyme, if you have initially 10, after the reaction you will regenerate 10. Therefore, there's no changes. If you were to say that, we're gonna measure the activity based on the disappearance of enzyme, since the enzyme did not change, the activity will be 0 or flat. Okay, but if you were to look at from a different perspective on the substrate, from disappearance of substrate or a formation of a product, then you can say that this enzyme has a certain activity that you can actually gauge, you can actually measure. Okay, and therefore to determine the concentration of substrate or product is by doing some of these. For example, you can do a titration. Maybe you can do a calorimetric titration. Okay, or when you did your, let me recall, if I'm not mistaken, analysis 1 during your second year, you did a lot of titration reaction, right? And these are, if you were to translate that into an enzymatic activity, those are the same thing that you are doing. Perhaps in your second year you are doing a catalytic activity on using metals, but if you translate, as I mentioned, enzymes are catalytic. Enzymes does catalytic processes. Similarly, if you use a metal catalyst for a reaction, then the metal is the catalyst. So if you consider E as a catalyst, okay, in this same process as a metal, so you can imagine the principle that you did for your second year analysis laboratory experiments. They are more or less the same. Okay, the principle are the same. Of course the calculation will be different, but so to say that you need to do a lot of calibrations and whatnot. Okay, so titration is more on your analysis lab. Additionally, what are the methods you can use? You can use absorption or emission spectroscopy. Okay, so it's more on photometric measurement, color. Okay, either a UV vis. Okay, so you can use a spectrophotometer, UV vis spectrophotometer, or you can also use fluorescence. Fluorescence spectroscopy. Why? Because depending on substrate and the product. For example, for UV vis, of course, most compounds do absorb light or UV at a certain wavelength, and fluorescence, for molecules that have unsaturated bonds, they are very, very susceptible to light absorption or a certain wavelength absorption. They might be fluorescence, they might not be fluorescence. So depending on the molecule, if it's fluorescence, then yes, it would be very nice to actually see that. Okay, and and if the product is involved, whereby initially they are frozen, and then once it goes through the changes from a substrate to a product, if the product is no longer frozen, then you can actually use that to measure the rate of disappearance of your substrate. Therefore, it will be the activity of the enzyme. Okay, and also some other examples are such as you can count cells. If the cells, you can count the rate of cell death, and then that can be as a form of your activity. Alright, so since activity or the formation or disappearance of product or substrate, okay, so that one is product, that one is substrate, is an act over time, therefore normally you will require a constant monitoring. So you cannot simply expect, since the reaction is E plus S forming P, and you know the initial concentration of S, say as I mentioned, probably X, Y, and Z, and then after a certain time, after say 1 day, okay, so X become now X prime, Y becomes Y, Z becomes Z prime. You cannot simply say, you cannot simply do this one, or just looking at that value and then say, oh, the activity is say 100. Because this one is a starting point, of course the concentration will be 0, the activity will be 0, and then suddenly you say it's 100. No, it normally doesn't work that way, because again, when we plot the enzymatic activity, it normally goes like that. Okay, if you do the Michaelis-Menten equation, remember why we are looking at the t equals to 0, or the beginning of the reaction. It's because the graph of enzyme activity is normally like this. Okay, it's skewed towards the right hand side, whereby that one is 100% activity. Okay, so it plateaus after a certain concentration, substrate concentration. So it will goes to plateau, and you can see that the activity, so to say, if you were to convert the whole graph into an activity, the activity on the towards the higher concentration is low, whereby the initial is high. So to just take an average of the whole thing, it doesn't really suit, because some people might use a different enzyme concentration, some people might use a different substrate. So there are too many variation. Therefore, what scientists normally do is to look at this initial phase, whereby the activity and the concentration is what's the word, it's not parallel, it's influencing one another. Okay, God, I can't remember the terminology on top of my head. So when you do this, okay, when you measure the activity over time, what you normally likes to measure, or what you normally would like to do, is to look at this initial bit of the activity. So that's why you do a constant monitoring, whereby you might, when you do your experiment, you might do something like that. Okay, you will get a value of activity, something like that, at a few time points, and then from that time points, you actually construct your plot so that you can get a proper graph, a straightforward graph that goes back to some photometric theory that we will look at after this. Alright, so this is a quote-unquote, the basis of an enzyme assay is a proper determination of reaction process. Again, reaction process from the first lecture of topic 2, or a concentration of reacted substrate. So concentration of reacted substrate. The concentration is converted into the amount of substrate that has been converted in the reaction mixture by consideration of the reaction volume. The volume of the sample is irrelevant, since the reference is the amount of enzyme that is applied. Okay, what does it mean by that? Then I will go through after I read the whole thing. Enzymes are usually applied in aqueous solution, buffered, and measured volumetrically. The activity of an enzyme can be considered as equivalent to a reagent concentration. that is a correlation factor of activity and volume that allows dosing of enzyme. Okay. Remember when you learned about this way back, probably in high school, okay? N equals to C times V. So N is number of mole, C is concentration, and V is volume. Okay, why does it say the volume is irrelevant? Okay, so this is because when you do this type of reaction up here, okay, the volume doesn't change. So that's why it's irrelevant. So for lab purposes, of course, if you're talking about an industrial perspective, then of course they has a different idea altogether, because doing an enzyme activity and to have a stop and go motion in an industry is it's not really what people do. Okay, in industry they like to have some activity or some reaction that is a continuous type reaction, not just you need to run it for 12 hours and then you need to stop for 12 hours and then you run it again for 12 hours. No, the ultimate goal for all industrial application is to have an ongoing process 24 hours 24/7, so that you can minimize your loss in time, loss in reagents and whatnot. Okay, again, for these purposes, if you were to do it in the lab, in a small scale lab, the volume is relevant. Alright, so the ones that I bold are part of the key important things. Other than that, it's not really that important. I mean, it's info, but yeah. Okay, so again, that one is since monitoring. Okay, look at that sentence. Also, since enzyme is recyclable, thus the activity reflects on the concentration of substrate. Okay, this one is the one that I mentioned previously. S plus E equals to P, E regenerate plus the product. Okay, so we will see this in the next few slides, and for this purpose we will look at absorption based assay as an example. So absorption assay, what does it do? It measures changes in the chromophore concentration. Okay, it's not really a direct measure of the concentration. It's more on you are measuring a certain amount of compound. Okay, because of course if you just use UV-Vis, you cannot actually measure the concentration directly. So because UV-Vis will just give you a value. If you recall your second year lab, okay, it will just give you a value 1 or 1.2, 1.4. So what you need to do then is UV-Vis. Never mind. I will talk about it down here. Okay, so some key information that you need to do or you need to know during your absorption assay is, first, you need to know the reaction. So you need to know whether it's a substrate converted into a product, and whether the substrate or the product is the chromophore, or just one of them is a chromophore, or you need to know whether the substrate will be consumed and degraded into something else, which is not even a product. So this is, for example, if you are doing an assay to look at antibiotic activity. Okay, antibiotic, say for example penicillin antibiotic. The activity of the mode of action for this penicillin antibiotic is to inhibit enzyme activity for cell wall formation. Okay, so that's the general idea. So the substrate is not being converted into a product. Okay, so we can consider that substrate moving to a degradation, because it will just degrades in the active site of the enzyme, thus blocking the activity of the enzyme. So you need to know the reaction of the whole thing. Okay, either you are focusing on the enzyme or you are focusing on the substrate or product. And then what you do is you measure the absorption spectra. So that one is related to that. so that you can know or determine the best absorption wavelength. So what do I mean by that? When you learn about UV spectrometer, I'm sure you guys learned that each molecule normally will have its own absorption spectra. Okay, we'll go that in more detail. So now I will just talk about it. So each molecule has its own absorption spectra. Whether it will be say if that one is 0 nanometer, this is just random numbers. Okay, so this is not an actual thing. And then that one is say about 8,000 nanometer, for example, even though it might go into a different band, but doesn't matter, because this is just an example. So that one is of course absorption. Some molecule will have an absorption like that, and others might have an absorption like that. So you need to, that's why I said you need to measure. So you need to do an initial analysis to actually know what is the wavelength or specific wavelength that you can use to measure the quantity of your all the components in the reaction mix. So basically you have three lah, of course, right? So you have the substrate, you have the enzyme, and you have the product. So you need to know this. And then once you know this, you will select a wavelength that is specific, or at least, well, more specific towards one of the two. Okay, one of the two meaning either the substrate or the product. As best as possible, you don't want to measure the concentration of the enzyme. You can measure it because you might want to investigate whether the enzyme is being consumed or whether the enzyme is being regenerated. So you might want to know the absorption of the enzyme as well. But because you are doing a monitoring, a reaction monitoring or enzymatic activity measurement, what you need to know is you need to know a rate of disappearance of the substrate or the rate of formation of the product. Okay, so once you know this wavelength, then you can choose. You can choose a wavelength that is specific for the substrate so that you can see the rate of disappearance, or the wavelength that is specific for the product so that you can measure the rate of formation of the product. You don't want to measure, or as best as possible, you don't want to use an overlapping wavelength that has both the reactant and the product, because if you do that, then you will not be able to see anything. Okay, we will go that in a bit more detail the next slide. And then once you know the correct wavelength that you want to measure, what you do first, if you recall on first year analysis lab, is to create a calibration curve. Okay, you don't simply just measure and then say, oh, okay, this one is XX concentration, or this one is 1 molar concentration. You don't simply do that. So what you do is, firstly, you prepare an enzyme or a substrate. So if you are looking at the, say, substrate disappearance, so you will set a certain value of substrate. So if initially, for example, you use 2 molar, which is very high, you might want to do a smaller ones so that you can get your calibration curve. So you might do 1.5, 1.0, and then you might have 0.8, 0.6, 0.4, 0.2, 0.15, 0.1, something like that. Okay, so so that you can actually see the rate, and finally you can hopefully draw a graph. Okay, so that one is formation of a product, so you might see something like that for substrate. Okay, and then from there you can actually calculate using some equations. Okay, so you can use Michaelis-Menten equation, for example. And so the calibration curve, what you will get is a set of points, and you can draw it in a straight line that obeys the Beer-Lambert law. Absorption equals to molar extension coefficient times concentration and times path length. Okay, distance of path length. And because distance are normally the same for everything, so and E, the excitation coefficient for a certain molecule, are normally fixed for a certain wavelength. So what we will see is absorption will be directly proportional to the concentration. And then from there, if you now measure your rate, then you can know, oh, this one is test concentration, that one is that concentration. Okay. All right. So to look at in more detail, knowing the determine the best absorption wavelength is first to ensure why do you need to do this? It's because to ensure minimal interference, so no overlapping peaks between the substrate and the product. Okay, I will draw the graph. So say for example, if your product has kind of like that wavelength, okay, let me see if I can change the color. Right, so if that one is the substrate, and then if your product has a wavelength like this, for example, okay, so the other one is product. So of course what you want is you want to see one of the well, minimum one. You can see both, of course. If you want, you can look at the rate of disappearance of substrate and rate of formation of a product at one go. But sometimes what you want is you want to see just one of them, or probably the molecules, the chromophore that you have is only just one of them, not both. So if that's the case, even though substrate and product in the figure that I'm drawing now, I'm showing that both substrate and product actually absorbs light at a certain wavelength. But sometimes what you might see is that the substrate does not absorb light at the UV-vis wavelength, but the product does. So you can just use any wavelength, that's for sure. But in cases where you have a substrate and a product whereby both has some similarities in the wavelength that they absorbs, then of course you need to be very careful in selecting the proper wavelength. So in this case, if you were to select a wavelength over here, then it will not be good, because both product and the substrate absorbs light at the same wavelength. So if you were to actually select this, say for example if this one is 100 nanometer, if you were to select this, what you will get is if say you want to measure the substrate, so you start off with substrate. Okay, so normally substrate is the higher concentration, product is a lower concentration. So a normal curve will look like that. Okay, so it will passes through in terms of the concentration, it will pass through between one another, so you can actually see it. But since your product and your substrate has the same wavelength, what you will see instead is the sum of these two lines. Okay, what you will see is just a flat line like that. Probably I should change color again. Okay, so what you will see is just a straight line, because as the substrate disappears, the product forms, and because they have the same wavelength, then you won't see any changes. In this graph, well, probably some might say, oh doctor, you can actually see changes because the substrate absorbs more light compared to the product. Yes, I know, I'm correct. You are correct in that sense. Okay, because the amplitude for the peak are different. But again, the main point here is that if you choose wavelength that has both substrate and a product, and they have high amplitude, okay, so this one are still high, so they are not down here, so they are still high. So what you will see is something like that. Of course, in this case, since product is which line, product is blue, so what you will see is a slight diminish of the overall absorbance. Okay, you will see a decrease, but the small decrease like that does not constitute or does not allow you to actually see what's happened. What you want is this is the optimal graph that you want to see. Of course, this one is before you do some rearrangement, and you'll finally get a straight line where you can really do calculation and whatnot. Okay, but that's other, that's a different theory. So what you want, if you move back to to determine the best wavelength, so what you want is you want something that has a lower. So if you want substrate and product, you either want the extinction coefficient for the substrate is low, the product is high, or the other way around, whereby the substrate is high, and the product is low. Okay, why do you want this? Because of course you can monitor it very easily. So say for example, if that one is 200 nanometers, that one will be somewhere around here. So I don't know if that one is 100, that one is 200, that one is about 160 nanometers, for example. Okay, this it's just a random number. Okay, so this is what you want. So you want a wavelength that can be more specific to one compound compared to the other. Okay, so that's the basic idea lah. Okay, so that you have this is what I mean by no overlapping peaks between substrate and product. Okay, and also because of this specific wavelength that you choose, it will require what you will do is you will minimize or you will maximize the sensitivity of the assay. Okay, sensitivity meaning that small changes in the substrate concentration, you can actually see it. Okay, so that's why you want to maximize the sensitivity. If you choose this wavelength at 100 nanometer, the sensitivity is lower. Okay, because the molar excitation coefficient for both substrate and product are high. Therefore, requires a small sample size, and also when you say maximize sensitivity, what you can do is also you can reduce the quantity or the initial concentration of your substrate, and still get a reasonable amount of output or results. Okay, what do I mean by that? I've drawn it already, so we'll skip. And the second one is when you do your absorption assay, of course you need to have a calibration curve, and a normal calibration curve that you do is absorbance versus concentration, so that and because it's an absorbance or UV-vis, you will definitely need to it will definitely fit into Beer-Lambert law and its application. Alright, so therefore it will fit this equation. Absorbance equals extinction coefficient times concentration times distance. And when you convert this into a linear form, as I mentioned, because that one and that is what do you say is constant, you'll get something like that. Until a certain point whereby the concentration is very high, you will see Beer-Lambert goes into plateau. I'll just turn on my Wi-Fi so that there won't be any disturbance. Okay, and once you have a concentration plot like this, you can actually directly measure the enzyme activity, whereby say for example at t equals to 0, you will have a value of 0.1, for example. And then at t equals to 30 seconds, you have a measure of 0.15, and so on and so forth, until t equals to say 1 hour, where you have an absorption of 1. So once you have this data, so this one is when you do your enzyme assay. Okay, that one is just a calibration curve, meaning that if you were to measure your substrate concentration, then you will prepare a substrate at a known concentration, as I mentioned, 0.2, 0.4. This is again an example. Okay, and then you're gonna plot it, do a straight line, and hopefully it's directly proportional, so that when you do your enzyme activity, when you receive the absorbance value from the machine, you can know, during this time, of course you need to do a second plot of activity, okay, activity and time. And then from there you can know, at t equals to 0, activity is like this, and then it's like that, like that, like that. So you can actually plot another graph. So that's how you actually do it. And if you recall, this is what you did in your second year analysis experiment. Okay, so you have learned this in your second year. And I think that's it for now. What will I do? I think we have another about 10 minutes. I will combine in showing you how to actually know all this information about EC value of the enzyme. And then, because I showed you PDB, protein data bank, multiple times, how do you actually use this? We have not touched that. I will just show you how to use those information, so that in the future, if you were to use it, then you know how to do it. Okay, I think that's all.